Welcome to Splitting the Email Atom, exploiting parsers to bypass access controls. Email addresses might seem mundane, but the RFCs governing them are downright bonkers. I'll show you why predicting an email destination is highly complex, and I'll take you on a journey of ancient protocols, exotic encodings, access control bypasses, and how I gained remote code execution from an RFC-compliant email address. First, I'll explain why email address parser discrepancies matter. Next, I'll cover the Shaky foundations on which they are built. The core of the talk will focus on parser discrepancies, including Unicode overflows, Encoded-word, Punycode, and all with real-world case studies. Then I'll share my methodology and tools for automating exploitation, followed by advice on defense. I'll conclude with the key takeaways and leave 5 minutes for questions. So this research all started when we realized that many websites use the domain part of the email address to infer the user's organization and apply access control. For example, Slack will automatically give you access to a company's Slack channel based upon your work email address. And Cloudflare zero-day trust can be configured to use the email domain to protect your internal networks. This makes email verification a critical security boundary. What could possibly go wrong? Everyone knows that URL parser discrepancies are critical, as they can lead to SSRF, path traversal, and other security issues. Using email domains for access control makes email address parser discrepancies critical too. Predicting which email domain an email should be routed to should be simple, but it's actually ludicrously difficult, even for valid RFC-compliant email addresses. So we've established why email address parsing matters. Now let's explore why predicting the email destination is so challenging. Email addresses are built on a shaky foundation of RFCs designed many years ago. Validation is often performed by copy and pasting regular expressions from Stack Overflow, all trying to follow the RFC. However, one mistake in the regular expression can bring everything crashing down. I'm not going to bore you with RFCs, but I will highlight the important ones for this talk. For instance, the characters before the @ symbol are called the local part. The RFC also allows what is called the quoted local part, which allows you to place characters that aren't normally allowed in the local part of the address. In this example, I use the quoted local part to use the @ symbol as part of the address. The same RFC allows you to use a quoted per, which basically means a character preceded by a backslash. This enables you to use the double quotes and the backslash as part of the local part address. Characters enclosed in parentheses are treated as comments and can be placed anywhere in the address apart from the quoted local part. When the actual email is delivered, the comments are removed. So here are 2 email addresses. You might be wondering which one of these emails are valid, as this is a typical question asked in an email presentation. However, it's the wrong question for this talk. The question you should be asking is which email domain does it go to? You might expect both emails to go to example.com, but that's not what happens. They both go to psres.net. Remember how I mentioned that predicting the email destination is extremely difficult? This is just the tip of the iceberg. The first example works on postfix, and the second example works on sendmail. If you are confused, you should be. A source route is a sequence of servers where an email goes through before reaching its final destination. Servers in the chain are separated by commas, and the final destination is marked with a colon before the recipient's full address. Another form of source routing is called the %hack. Despite its name, the actual character is chosen by the mailer. In this process, the email is initially sent to example.com, after which the % symbol is converted into an @ symbol, and the email is sent to foo@psres.net. This process can be repeated several times. Before email addresses and even the internet existed, people exchanged messages using the UUCP protocol, which is a Unix to Unix copy protocol. UUCP is an early protocol that separates the local and multiple hosts with an exclamation mark, creating what is known as a bang path. Unlike the standard format for emails addresses today, the bang path lists the hosts from left to right, with the final destination user mailbox at the end. So going back to the original examples that I gave, with all the special characters removed, the parentheses effectively remove the @ symbol and the domain, and without the domain part, PostFix treats the email as a % source route. Using a / and escaping the @ symbol has the same effect on sendmail, which treats the email as a UUCP address. Pretty damn crazy, right? And I have checked, and all those special characters do go to the email mailbox. So this is just the examples with them removed. I wish I could tell you that I uncovered this behavior by analyzing thousands of lines of code, using a debugger, and stepping through the code flow in SendMail and PostFix, but that's not actually how it went down. I noticed that an unnamed target was allowing all sorts of special characters. So I took them all and pasted them into my email, expecting them to fail. But instead, I checked the syslog on a box I was testing, and I noticed a difference. I was getting host unknown error in the delivery status notification. This was significant because it would suggest that a different host was being used. And if you look at the error, you'll notice the exclamation mark was missing. I didn't actually notice that at the time, but that was a clue. I started to remove characters and resend the email to see if I could get the same message. I narrowed it down to the exclamation mark and thus discovered the UUCP behavior. This was bonkers. By sheer luck, the characters I pasted ended with a /, which escaped the @ symbol, and then I wrote a fuzzer to find the source roots behavior, to find the behavior in PostFix. These findings gave me great confidence that there were tons of bugs out there, so I began to look for more. One of the main problems I had with this research was to generate blocked characters. Many applications will block multiple @ symbols. So this following section focuses on Unicode overflows, which enable the creation of ASCII characters from higher Unicode characters. The PHP char function is a good example of how a Unicode overflow can occur. This function generates a character from an integer code point. Here's an illustration of the algorithm used by this function. It loops through the code point while it's less than 0, continually adding 256 until it's non-negative, because why not? This is PHP after all. Then it uses a mod operation to ensure the byte value is always within a range of 0 to 255. It will be truncated into this range. Note that Unicode overflows aren't specific to PHP. Generating a Unicode overflow in JavaScript is quite simple, using the fromCodePoint method. First, you pass the number that you want to cause the Unicode overflow, such as OX100, which is 256 in decimal. Next, you'll provide a second hex number to specify the actual character you want to generate, like OX40, which is the @ symbol. The fromCodePoint method will generate this Unicode character, and then when that character is transformed to fit within 255 by a system that doesn't support higher Unicode characters, it will produce an ASCII character specified by the second hex number. So I started hunting for real-world Unicode overflows, and I found a target that I don't really want to mention because it might get hacked, that alters the characters within the mailer's SMTP conversation. The application blocked the backslash in the quoted local part, but I bypassed this validation using a Unicode overflow. This enabled me to escape characters that aren't normally allowed to be escaped and break out of the quoted local part. Despite this, when using an encoded art symbol, the email wasn't sent, suggesting there's a double validation, once in the application and once again before sending. So although I didn't manage to exploit this particular target, the key takeaway is that Unicode overflows can be used to bypass validation and smuggle characters within the actual SMTP conversation. So Unicode overflows were great, it's a cool technique, but I needed more methods to generate blocked characters. So I took a deep dive into the glorious RFC, looking for gold, and I found it. This next section is about encoded-word. I discovered this when trying to find ways of generating the art symbol without Unicode overflows. Encoded-word is specified in RFC 2047, and it allows the inclusion of Unicode characters using encoded data. And this is how encoded-word works. Equals and question mark indicate the start of the encoded word. Following that is the character encoding, in this case UTF-8. The question marks act as separators between the encoding type and the character set. Inside the separators is the encoding type, in this case Q encoding. After that is the hex encoded data. So equals 41 represents the uppercase character A. Question mark and equals end the encoded word. Once the email has been parsed by the email parsing library, the encoded characters will be converted, and the encoded word meta characters will be removed, and then it gets sent to that following email address. Pretty damn crazy. To probe for encoded word, you should make 2 requests with these 2 char sets. The reason for this is because different email parsing libraries support different char sets. When probing, you should use lowercase characters to detect if the site rejects or transforms to lowercase. Initially, I was using X as the char set to reduce the size of the probe. However, this will be rejected on some systems, so it's better to use these 2 probes and then follow up with X as a char set if it works. If successful, you should get an email to the emails displayed. In a real probe, you will probably use a collaborator payload or similar. I've highlighted the encoded and decoded text in red. So we've covered how encoded word works. Now let's dive into some real-world case studies. The following case studies all use RubyMail, which is a Ruby library, which has over 508 million downloads. At the time of testing, the version was at 2.8.1. This library is used by many popular Ruby applications, including GitHub, Zendesk, GitLab, and BugCrowd. For my first case study, I'm going to show how I exploited GitLab Enterprise. So first, you can use X as a char set, as GitLab in this particular instance didn't care about it. I could then use an encoded @ symbol. And then I used an underscore character, which in encoded word is treated as a space. So you can use a hex encoded equals 20 as a space or the underscore character. And then what happens is the email gets split in half. GitLab thinks the domain is example.com, but it actually gets sent to psres.net. So it results in an email to collab@psres.net. So what was the impact of that? Well, I could verify email addresses that I don't control. This means I could gain access to GitLab enterprise servers that had domain-based email restrictions. To understand the next set of slides, let's have a quick recap on how an email is sent at the SMTP level. There is a conversation and handshake between the mailer and the SMTP client. It does the handshake, but the important part for this is the receipt to command. You'll notice the email is enclosed with angle brackets. We're going to abuse these in the next slides. So GitLab is also an IDP, so I exploited the email verification. So this is separate from the enterprise products because they use postfix by default. So I used X on the slide, but you need to use that following char set because it wouldn't fit on the slide, and GitLab will reject any unknown character set. So you need to use that char set. I then used an encoded @ symbol again. And this time, this is the interesting part. You can use an encoded greater than symbol, as I showed you on the previous slide with the receipt to command. And this allows you to ignore the rest of the address, provided you've got a space. So the greater than symbol is used. I used an encoded space, and then the email is sent to psres.net while GitLab thinks the domain is example.com. Using this bug, I could bypass domain-based access controls who used websites on websites that support GitLab as an IDP. This screenshot shows that I've got verified domains from Microsoft.com, GitLab.com, etc. I could verify any domain. This next technique is a more complex attack that worked on Zendesk. And it uses the quoted local part with encoded quotes. First, we use a quoted local part with the double quote. Then we use the Q-encoded double quote. So that's a hex escape double quote, followed by an @ symbol. Next, we have a greater than character to finish the receipt to command, as I showed earlier. And after that, this time, I use a null character. And I use this to ignore the rest of the address. Due to the quirks of the mailer, the validation that Zendesk used, I had to use an encoded less than and double quote. This was removed by the Zendesk validation and parsing. Then I finish the quoted local part, and the email actually gets sent to collab@psres.net. It's absolutely insane, really, how this works. So, yeah, what happens is all this gets decoded, and Zendesk removes the quoted local part because it's trying to make sure it doesn't bypass its validation or whatever. And then it removes all the characters and then sends to that email address, whereas Zendesk still thinks it's example.com. So the impact of this was attackers could verify email addresses from domains they don't control, which means you could get access to Zendesk email domain protected support centers. GitHub were also vulnerable to the greater than and null attack that I've previously demonstrated. So first, I created an encoded @ symbol again. Then I used an encoded greater than to end the receipt to conversation. Then you can use an encoded null, and then the rest of the address will be ignored, which results in the following email. So yeah, it's pretty damn crazy to think people will trust GitHub's email validation. You really need to verify that before you use it. So using this technique, I was able to verify any domain I liked on GitHub. And I had verified emails from Mozilla.com, GitHub.com, and Microsoft.com. By spoofing email domains on GitHub, I could verify addresses from domains I don't control. This allows me to bypass domain-based access controls on websites that use GitHub as an identity provider. For example, I could penetrate internal networks protected by Cloudflare Zero Trust, configured with email domain validation. This screenshot shows Cloudflare Zero Trust, trusting email domains from github.com. And since any domain can be spoofed, this affects all Zero Trust instances that use email domain validation. So don't solely use email domain validation. As I was testing multiple Ruby libraries, I discovered you could also use base64 encoded email addresses. Because why not, right? We need this. What could possibly go wrong? In this example, the B indicates the start of the encoded word type. So this signifies a base64 encoded type in encoded word. Then we've got a base64 encoded address. So in this instance, I've encoded foo bar, but it works with any character. I've just used foo bar as an example. And that results in an email to that address. So that you can embed arbitrary characters, whatever you like, in the base64 encoded email part. Anyone remember this? This is a UTF-7 encoded script block that used to work in IE. I loved UTF-7. Surely the email parsing libraries won't allow you to use UTF-7 charset. Of course they do. Using the Ruby library mail, here is a UTF-7 encoded address. So this is a UTF-7 encoded foo bar, and the charset will be decoded, and it will be sent to that email address. I know what you're thinking, or maybe it's just me, but yes, you can use a UTF-7 address and a base64 encoded address within one email. In this example, there is a base64 address with a UTF-7 charset. So first, the email parser will decode the base64. Then the email parser will decode the UTF-7. Absolute insanity. And that results in an email to foobar@psres.net. But yeah, you can use double encoding. You can use a double base64. So it's like a base64 address and a UTF-7 address. And you can encode arbitrary characters. It's just not restricted to alphanumeric characters. Then I thought, what about a mixture of UTF-7 and Q encoding? So here I'm going to modify the A character. So I'm going to encode it with =41 as hex. And then this gets decoded in the second level, so then it gets treated as a base64, as a UTF-7 encoded address. Base64 and UTF-7 are similar anyway, but the first part is an encoded, Q encoded =41. It gets decoded, and then that's a UTF-7 address charset, which gets decoded, and the email gets sent to foobar@psres.net. At this point, you might have a few doubts about following the RFC to the letter, especially when I tell you that this works in the domain part when I tested the mail library. I know what you're thinking. Nobody is going to support UTF-7 encoded emails. Well, it worked on a small source code hosting website called GitHub. I was gutted I didn't exploit them with this because I'd already exploited them earlier. So it would have been nice to have a UTF-7 exploit, but who cares anyway. So after that, I went hunting for encoded word outside of Ruby. And I found that PHP Mailer supports encoded-word within the name of the recipient. I tried exploiting WordPress and other applications, but the requirements of needing angle brackets around the email made exploitation difficult. Still, I bet there are a lot of systems out there that reflect the name and then they could be exploited for XSS, for example. So it's worth having a go trying to see if the name part of the recipient can be decoded. So we've already explored how you can manipulate email parsing to sidestep access controls. But let's take things a stage further. What if you could weaponize an email address to gain remote code execution? Well, in this next section, we'll cover Punycode attacks and how I exploited Joomla. Punycode is a way to represent Unicode characters in the current DNS system. Punycode always starts with XN and is followed by 2 hyphens. The algorithm converts the sequence of Unicode characters into a representation that utilizes only alphanumeric characters and hyphens. For example, the domain muchen, as shown, is encoded with the following Punycode sequence. The very nature of how Punycode works makes it difficult to test because if you change one character, it can affect the output and the character position due to how the algorithm works. What you want to do is generate malicious characters that when it's decoded, but doing that is a really big challenge. In these examples, you can see the position of the Unicode character changes when 1 byte is modified. So you can see the Unicode character moving along as you change 1 byte. So after reading about Punycode on Wikipedia, I followed a link and began testing on an online Punycode converter and began to experiment. The converter used the buggy IDN PHP library. I started adding zeros to the beginning of the Punycode address to convert it into ASCII characters. I initially succeeded in generating a comma, which I was so surprised I doubted my eyes. Encouraged by this, I started to experiment a bit further and produce the @ symbol. So here you can see the Punycode address on the left and the decoded address is on the right. So after searching GitHub, I found an interesting target using this library, Joomla. This was great because if I got XSS, then I don't have RCE. Doing source code analysis, I noticed they were escaping the user's email address before it was Punycode decoded. This means if I could produce some malformed Punycode that when decoded produces HTML, I could get XSS. But it wouldn't be that easy. So here I'm displaying they've escaped the email first, but then Punycode decoded. So this is why it works. You get some malformed Punycode, and then you'll get some malicious characters out. So it sounds simple. Just give the decoder some malformed Punycode, generate some HTML. But remember how the algorithm works. Any change in the character can result in a completely different output. I thought this was a job for a fuzzer. So I just wrote a simple fuzzer to generate malformed Punycode. And the results were really interesting. I found many ways to generate different characters. So on the right, you can see what I'm trying to do here. I'm trying to generate an SVG tag, and then maybe an event, maybe quotes, that sort of stuff. So I started generating millions of different character combinations. I managed to construct partial XSS vectors, but I encountered several issues. I could only generate 2 ASCII characters by using more than 1 Punycode subdomain. This limitation arose from the specific workings of the Punycode algorithm, PHP, and the quirks of the PHP IDN library. As you can see in the examples, I was really close, but these problems made exploiting Joomla very difficult. I concluded that XSS was not feasible because although I was able to generate a single quoted attribute, it required an underscore character. Joomla, however, does not permit underscore characters in the domain part of the email address. So was that the end of the story? Well, not quite. I thought about this for a while, and I worked out that you could use a single Punycode subdomain, and then you could generate any opening tag. Eventually, after a lot of testings, I concluded that the only exploitable vector was an opening style tag. Here I use malformed Punycode to construct it. This is not a test string, that's the actual value. So the Punycode library decodes that as a style tag. What happens with the injection is the rest of the pre-existing Joomla HTML code would add the space and the angle bracket for me. So you can see the malformed Punycode is added to the output, and the TD tag in the Joomla code will add the greater than for me. So you've got a valid style tag, and this will work fine in Joomla. So I'd need two accounts. The first creates a style tag with the malformed Punycode, as previously demonstrated. The second account contains the actual CSS payload, which is inside the name field of the user, and that imports the malicious style sheet. The first account name starts with an A because I want that one to go first, and the second one starts with X, so the import gets done second. This is to ensure it starts first and then second. If you notice the curly braces, this is because all the rest of the HTML is treated as an invalid selector. Because why not? This is CSS. So like all the HTML that occurs before the injection will be treated as an invalid selector and completely ignored. And in Chrome, they fixed this by using strict MIME-type style sheets. But with the style tag, this does not apply. This is why it works. So as I said, the first step is for an attacker to register two accounts. The first with the malicious Punycode, and the second with the evil embedded CSS in the name. So all that's required is two accounts, and Joomla does not, you don't even need to approve these accounts in order to exploit. So the attacker uses import chaining and a custom node-based CSS exfiltrator server to quickly exfiltrate the CSRF token. When the admin visits the user's page, you've got persistent style injection. So the malicious CSS is loaded and the token is extracted. And this screenshot demonstrates extracting the token. Using the exfiltrated token, the attacker then uses the CSS exfiltrator and gives the admin a URL that performs a CSRF attack and then modifies the admin template to get RCE. So this is the attack flow once the token's been extracted. I'm actually going to demo this now. James convinced me to do a live demo, so here, let's give it a shot. So first, we have got the exfiltrator server. This is going to be damn tricky. Right. So the victim, the admin, is on the left, the left browser. The attacker is on the right. So the attacker's first step is to inject all the malicious Punycode. So I'm registering one account with the malicious Punycode. So I get an error because I haven't configured mail, obviously, but we don't need mail. And then the attacker then registers a second account in the name, so that contains the styles. So we register the second account. Cool, so far so good. And then this is the CSS exfiltrator running on a Node server. So now, not a lot of room, to be honest. Hang on, there we go. So now the admin visits the admin page and then logs in. And then we go to the users page. The exfiltrated token is extracted from this persistent style injection. And then we start to talk to the admin now. Hi, admin, how are you doing? I'm doing great, how are you? Living the dream, etc. So they're just going to click on the link. The link then applies this backdoor. If you can see the code there, you can see the backdoor. It just checks the get parameter and then cats, etc. password. And then the attacker visits that backdoor, and we've got RCE. Woohoo! Thank you. Whew. So when conducting this email parsing research, I found it useful to follow the following methodology: probe, observe, encode, exploit. First, you probe for encoded word, observe the decoded email to confirm that it's supported, then encode the various characters and observe that they are decoded. Then follow up with an exploit that abuses these characters. I've done a little example of them following the methodology there. So in this case, I'm trying to see if Q encoding is supported. So Hackverter is a free open source tool that I've wrote for Burp Suite. I've crafted some Hackverter tags to help generate Unicode overflows and encoded word attacks easily from within Burp. Turbo Intruder is another free Burp extension written by Germs Kettle. I've created the Turbo Intruder script to help exploit the mailer. This script is used once you identified that the encoded word is supported, but you want to know what characters can exploit the mailer, like null, for example, space, whatever. For ease of use, we've also built this into a Burp Intruder word list. I've also created a Punycode fuzzer that can help find malformed Punycode. The fuzzer works with, you just give it some Punycode input and then add the placeholders, and it does some, it has like random substitutions and characters and white space. It was really effective in finding what characters were allowed with malformed Punycode. To defend against email splitting attacks, just make sure you filter out or disable encoded word. Always verify email addresses before using them, even when received from an SSO provider. After validating the email address, do not use the domain as a sole means of authorization. That's my advice. A few blog posts were really inspirational when conducting this research. I really recommend you read each one because they contain really useful information. The import chaining technique that I used to exfiltrate the token is from Pet Villa and Donut. If you enjoyed this presentation, you might also like my colleague Martin, who's doing a talk on web cache deception and web cache poisoning, and it starts at 10:20 tomorrow. So the three takeaways that I want to leave you with are: valid email addresses can trigger major parser discrepancies. Even addresses that end in @example.com might go elsewhere. As a result, it's never safe to use email domains for access control enforcement. We've created a web security CTF to help practice your skills, your email splitting skills. I've also, for your convenience, created a Docker file with the vulnerable version of Joomla so you can try these attacks out for yourself. You can get all the links and all the materials from this talk on our GitHub repository. Thank you so much. Any questions? Yeah. So the question was, did I get any backstory of why the RC allows this nonsense? I think it's mainly to support like accent characters, like Spanish accent characters, that sort of thing. That's my take on where it comes from. But yeah, it's absolutely insane. No, not UTF-7. So like I was specifically talking about encoded word. But yeah, you could have like Unicode characters embedded in UTF-7, I suppose. But why they would need UTF-7 as a char set in an email, I have no idea.
Have you spoken to RFC authors or the Internet Mail Consortium?
No, I haven't. Sorry, I can't see where you. All right. Oh, no, I haven't. I haven't spoken to them. No. But yeah, somebody really should.
Test. Test.
Cool. Thank you.
One more question.
Oh,
please.
yeah.
On the left. Left here.
Oh, yeah.
Could you quickly speculate where else you might find this issue, like email clients, cert validation, etc.? Thank you.
So the question was?
Where else might you find this issue?
Where else? File uploads, that sort of thing, maybe. Maybe you could use it within the name part of the recipient as well. So I think, like, when an email gets sent from Google to somewhere else, and they decode that data, and then it gets sent somewhere else, and maybe you could potentially exploit that in some way. So yeah, that's one potential exploit.
Thank you.
I didn't even try XSS, by the way, because I'm bored of it, really.
I have another one.
Yeah?
On the right. Have these vulnerabilities in GitHub and Cloudflare been fixed?
Yes. So GitHub have fixed it. Cloudflare was not reported as a bug because it wasn't a bug. It was a bug in the way that GitHub validate their emails. So if Cloudflare wants to just use email domain validation, I can't really put that as a bug because that's just what they do. But GitHub had fixed. You can't verify emails using the techniques I've shown on this on the slides.
Thank you.
No worries.
And
cool. Thanks. Thank you.